All right, physics. Quick little lecture here on mass spectrometers, which is a very cool machine that can produce a mass spectrum, which I'll explain in a second. But before I do, I'm going to tell you a true story. I was at university one day and I was in the library studying hard, and I noticed a little bright speck in front of me. And when I picked up that little speck, looked like a shard of glass, to be honest, I noticed actually it was a very well cut stone. It was smaller than that one that I've got pictured there, but it was definitely a little tiny diamond type thing. And I was like, ooh, I wonder if I've got a diamond. Knowing that diamonds are really, really hard, I grabbed out two 20-cent pieces from my wallet and I put the diamondy thing between the two 20-cent pieces and I pushed as hard as I could to see if I could crush it. I knew that if it shattered into little pieces, there's no way that thing was valuable. But when I did it, it didn't break. It just put two dents in my two 20-cent pieces. I was like, ooh, this is a hard stone. I wonder if it is in fact a diamond. So I went over to the physics department where they have some mass spectrometers. These are some of UWA's actual mass spectrometers. That's what they look like. And what they're able to do is you put in a small sample of stuff and they will spit out a graph like this, a mass spectrum. Along the bottom here, check out the axis, it's mass per atomic mass units. So basically this is, along this x-axis is the mass number. And if you know roughly what you've got, you can figure out this particular sample must have had quite a bit of platinum, which would have been really cool to find in the university library. Platinum is really expensive and quite valuable. So I was hoping to see a spectrum like this. It tells you like this, the ratio of atoms that you have going on. I was hoping to see a spike right on 12, mass per U12. If I have a big spike on 12 and not much else, I know I've probably got carbon 12 diamond going on. They never let me do it though, so I never really found out. So how does this thing work? How do you get this spectrum that, I mean, you've got to appreciate the coolness of this graph, by the way. Like, it is separating platinum 194, platinum 195, and platinum 196. It's showing you it can differentiate between 1 neutron's different in your sample and tell you the exact ratio of isotopes that you have. Like, it's a really precise, cool machine. How does it work? Zoomed out view, you chuck your sample in this little chamber and an electron beam will zap your little sample that you put in there and knock off electrons from your sample. So leaving your sample with a positive charge, and then it will be attracted to this negative plate here. There'll be a little hole there like we saw before. And then it'll be accelerated in this little gap here. This is what's called a velocity selector. So they just pick up a whole bunch of speed here. And then it passes into a magnetic field, and we know what happens when charged particles enter a magnetic field. They experience a centripetal force, and then we direct them towards this detector over here, and the beam is spread out. I want to take this one part at a time. So I don't really know how this ionizing thing works. We don't need to worry too much about that, but this region here, this velocity selector, is something that we want to learn the physics of. So the velocity selector, once you ionized your particles and you speed them up, accelerate them, they pass through this velocity selector, which is a parallel plate, electric parallel plates at right angles to a magnetic field. So I've got an electric field and I've got a magnetic field at right angles to each other. So my positive particles will, as they fly through, they will be pushed downwards by the electric field. And if you get your right hand out, move your thumb facing to the right, and that field is going into the page. You can see that they would experience an electric Lorentz force, upwards. So we've got a QVB force up and a QE force down. Now, if the particles are going really, really fast, that QVB force is going to be strong, and it might be so strong that it gives it a net force upwards, and the particles will take a path like that through the velocity selector. If they're going a little bit slower relative to the other particles, the QVB force is going to be somewhat weaker because it depends on velocity. And so those particles will be deflected downwards as they go through. But there's going to be some particles that are going at just the right speed, such that they go through this thing in a straight line. And if they go through in a straight line, you know for sure that the force up must have been equal to the force down. So QVB must have been equal to QE. And so what we know is anything that passes directly straight through must have had a velocity equal to the ratio of the electric field divided by the magnetic field. You can do that math for yourself. Force up equals force down. So basically this machine filters out particles so that anything that passes through it in a straight line, you know that it's traveling at this exact speed, which is determined by your setup, your electric field and magnetic field. It doesn't depend on mass, doesn't depend on anything, it just depends on those two things. It's pretty cool. So it's a velocity selector. So then all the particles that pass through in a straight line, then we send them into a magnetic field, all traveling at the same speed, but when they pass into this other magnetic field, then they experience a centripetal force. And we saw the other day that's going to be put them into a circle and spread them out. So they're traveling in a circle, so we know that the net force on them is mv squared on r. We know what is providing the net force. The net force is being provided by that QVB force as they fly into this magnetic field. And so the path that they take, that circular path, the radius of that path, rearranging for r, is equal to mv on qb. Now they all have the same velocity. They're all passing into the same magnetic field, and presumably they all have the same charge because they would have all lost one electron. And so the only thing that determines their radius is their mass. If they have a big mass, they're going to have a big radius, right? They have a lot of inertia, so it takes more oomph from that QVB force to pull it around. So the heavy particles land over here and the light particles over here. And it basically spreads out the particles according to their mass. And this here is going to be a detector that registers little ions hitting it. You can count them up. So the math of a mass spectrometer looks something like this. You know, if you ionize it, send it through the velocity selector, and everything that passes through the velocity selector has a known velocity of E on B, where B is your magnetic field in the velocity selector. Then it passes into this magnetic field. They all get bent around in a circle and hit the detector. And so what the mass spectrometer does similar math. It's going to go, oh yeah, it's in a circle. QVB, where this B is, of course, this B over here. No, wait, that's not that B. That B, sorry, this B is this B here. The bendy force inside the magnetic field. Rearrange for M, and all of these quantities the mass spectrometer knows. So it knows the charge, which is +1, knows the magnetic field, this one here, because we built the machine. The radius is given by the detector, like how far away did you register that little event, and we know the velocity. So we know all these quantities, and so the machine can spit out the mass and tell us how many little mass that mass particle landed just here, sort of thing. What have I done there? Oh yeah, cool. I just subbed in V equals E on B. Gotcha. Ta-da. That's the mass spectrometer math. Yeah, so that's how they work. It's pretty cool. So you can determine what's the molecular makeup of your samples. Here's the work that you guys need to do to practice that. Happy quarantine.